Thank you for that, Abel. So I see we have 6 members joined. Maybe we can just start. What do you propose, Abel? You can see the 7th one.
Let's start.
Okay, thank you. So yeah, good afternoon, members. My name is Robert Ofwete from Kenya, and this afternoon we're going to discuss. It's a discussion session, a practical sort of session on how to build and describe a compartmental model diagram. What are the important components or other key components to consider when building a compartmental model diagram? And how do you define the transition parameters? What goes into the transition parameters? So on and so forth. And for the sake of, I think I can touch on, even though I haven't highlighted it, I can touch on how then we can bring in aspect of intervention, some of the possible ways in a compartmental model diagram. And just to start us off, this session is a spin-off from the morning session. So some of these terms and some of these things that we're going to see will be repetitive, but that is good because it actually emphasizes on the importance of some of these key concepts when it comes to mathematical modeling or dynamic modeling of diseases. So what are some of the terms that we use to describe individuals in transmission dynamics? From the morning session, we saw some of the compartmental models that we can have. One of them is SIR. We have SIR, which is considered as the basic, but we have a susceptible and infected only model, SI. We have SIRS, where we have the recovered going back to the susceptible. And we have SIS. And you'll do well to remember that the key difference between SIRS and SIS, is that the R denotes some sort of immunity post-recovery. So if the disease that you are modeling in this case has, or rather confers immunity for some period before an individual goes back to the susceptible, then you are better placed modeling the disease using SIRS as compared to SIS. But then if your disease doesn't confer immunity, then and this individual is susceptible once again after being infected, rather immediately as soon as they recover, like the case in point of gonorrhea, which was actually touched on by Sylvia, then you're better off using SIS model. So susceptible in this case are uninfected, but they are able to become infected if exposed to the disease by getting into contact with those who are infected. So if you think of a case like which one? If you are talking of road accidents at a particular time or other day of the week and time, let's say Friday evening, and that Friday evening you are indoors, then you're not susceptible to road accident because we are looking at road accident specifically. So exposed, they have caught the disease but are not yet infectious. They're incubating the disease, so the incubation period. And for me, I don't have much exposure with regards to SEIR models, but I like the minimal exposure that I have. I like referring to this as seroconversion. So seroconversion is a period between when you're infected and when antibodies come up against the disease. So that's such that when you're actually tested, someone can actually detect an antibody, or rather the antigen, active in the system. So that period between infection and seroconversion then is an exposure. And then when you've seroconverted and now you start showing clinical signs, you can infect other people. And then we refer to that as the infectious period, or rather you're in the infectious stage and stage. So infectious is infected and can transmit the disease to any susceptible individuals as they get into contact. And remember, something else that is important is that for someone to move from the susceptible to the infectious, they have to come into contact with a person who can actually transmit the disease. And that is why the DSDT has had negative beta SI and not negative beta SE, because the E at this state, they cannot transmit the disease, and therefore they cannot successfully lead to someone leaving the S to the E compartment, but rather the I is the person who can actually make the S susceptible individual leave the S compartment. We have the recovered from the disease and acquire a long life immunity after infection. So if it's an SIR, that means you can never go back to the susceptible. There's a lifelong immunity. We have diseases like, say, measles. We have diseases like, say, chickenpox. Once you recover, it is believed that it is hard or next to impossible for you then to contract the disease again. They offer long life immunity. But then if the disease offers temporary immunity, as we've said, you'll have to add an S. And just a spanner into the works is that they say rather than having two S compartments, as we've seen in the examples practical session from Sylvia, you'd rather have an arrow from the R to the S. There's no need of adding a second susceptible compartment because the susceptible person is the susceptible person. So you can't be here and here. The compartments have to be mutually exclusive of each other. So latent infection implies presence of infectious agent, but absence of clinical disease. I don't know much about that as well, but I tend to think of it as an asymptomatic state where you can transmit, but clinically you don't show the disease. And we have individuals like that as well, who are important. So then the next step is to think of the types of mathematical model. We've heard of this static, dynamic, deterministic, stochastic. What defines all these terminologies that we hear? Someone will tell you, I actually did a stochastic model on this, and it showed that the infectivity rate varied from this level to this level. While a deterministic model, someone will say, I did a deterministic model and I used this rate. So what defines these variations in the types of the dynamic models that we use, or other mathematical models that we use? So a static model, as the name suggests, or rather alludes to, does not account for the element of time, while dynamic model does. A dynamic model is basically what we use. I haven't seen a static model. Oh, I've just seen one logistic growth curve model for fish population in fish ponds, fish farming. But mainly, we just do dynamic modeling of diseases where we consider aspect of time so that then we can be able to predict, we can be able to advise on disease preparedness, outbreak investigation. So dynamic models typically are represented with difference equations of differential. So we have difference equations and we have differential equations. We'll see what those are. Deterministic or stochastic. A deterministic model is one in which every set of variable states is uniquely determined by parameters in the model and by sets of previous states of these variables. So variable states are actually the compartments in this case. Some people call them the such variable S, I, or R. Some people call them the compartments. And in deterministic, think of it as modeling the average scenario. Case in point, let's think of a disease like COVID, where we are saying that the force of infection was 0.0017. That is on average. So you took a force of infection in high infectivity areas or other seasons vis-a-vis the low, and then you got average. And that's normally what we see commonly is people get these parameters from literature, and they get the average, and then they tend to model based on the average scenario. What does the disease dynamic look like? But then in stochastic is where now randomness in these parameters are actually investigated. And here we use probability distributions. So we say even though it's a 0.7 or 0.0017, we have randomness in this value. It can vary. And that is actually what happens. I remember someone asked a question that the parameter model was set as a fixed value, but then it can always vary. In a real case scenario, your susceptibility, how susceptible you are, differs from how susceptible I am to that disease. And then stochastic model tries to look at these dynamics and take account of them. And therefore it uses probability distribution. Then just something to add on to that is that then if you're talking of parameter estimations, parameter values, these values that define transition rates, transition from one state variable to another, we have several approaches that we can use to estimate this. One of the basic ways that I've commonly done is literature review. You want to see in similar environments or other similar scenarios, what were the rates like? What were the values like? What were the parameters like? And then you check them and you get the average for deterministic, or you use them all for stochastic and specify, because you have now all these values. You can use frequentist approach. Most commonly, we have the maximum likelihood estimation. So you just want to come up with this value that you'll use it if you have data. So if you have data and then you have prevalence out of that, we say that 30 over 100 people are infected. And then you assume that the infectivity rate is 30 over 100, which is 0.3. And then you have that defining transition from the S to the I. You can use Bayesian approaches, where you have prior information and you want to fit into that system to define your parameter values. And then that will definitely give you the probability distribution. Deterministic equations. So we saw that we had difference or differential equations based on dynamic models. So deterministic equations are either difference or differential. Difference equations are used for discrete time steps. So you are modeling days in days or months. You want to see which month, especially for people who model for seasonality and cyclicity. And then you want to see this disease, for instance, malaria, associated with rainfall seasons or just post-rainfall seasons. And you're interested in the months. Maybe others want to see the days. But in other people, they use differential equations. And this tend to reduce the time steps to very minimal. It can't be zero, definitely, because that's not sustainable, but as close as possible, so that you want to see changes in a very minimal change in time event. So this is not important per se, but it's just knowledge towards spanning into the works that sometimes we do refer to, but sometimes we do refer to them interchangeably. So then what are the key steps when we're setting up a model? When you want to decide which model to use in a disease, and that is always the first step. But then the first question is to ask yourself, does a dynamic model is it really important in this disease? Maybe at times you just want to use a statistical regression model, and that will adequately meet your answer, or rather respond to your question. But sometimes we have to use a compartmental, rather dynamic model to be able to see all these what ifs and simulate different scenarios and answer different questions. And that is why dynamic modeling is very important and paramount when you're modeling for policy, because you can't go to the field all these times. But if you have a set of differential equations that then can actually model the dynamic of our disease transmission in an environment, you can then try to think of other scenarios. What if we have more susceptible? What will be the number of infections like? What if we vaccinate 45 instead of 70? Let's say, for instance, the BCC intervention, behavior change communication intervention, is not working. And people are actually estimating its performance as 70% or rather 30%. What if then we change its effectiveness to 30%? So that means that we have more people who are getting susceptible. And what if people don't go to the hospital? What number of recoveries are we going to have, and what number of deaths? What if we bring up public health awareness and tell people that if you're actually bitten by a snake, you need to seek medical care, or rather hospital care, and not traditional care? So if we have 70% moving towards the hospital compartment, how many deaths are we going to get in the hospital vis-a-vis the traditional compartment? So all these scenarios, dynamics, the strengths are what we refer to as the strengths of compartmental or rather dynamical modeling. The first thing is to identify the question. Definitely that is the first key step. You have your project at hand, you have your program at hand, you have the disease of interest at hand. So then you identify the existing or relevant facts. And here is what we are referring to as the epidemiology of the disease. Sometimes, if not all the times, you also need to work with the biologists to understand the pathophysiology of these agents within the host, if it's a disease that is infectious in terms of person-to-person transmission, or even within both the host and the vector, things like malaria. You want to actually understand how does this plasmodium behave, how does this schistosoma behave within the snail, so on and so forth. So those are very important. And then you choose the model structure. If most of the diseases, not all the diseases have an exposure period. So you get from S to I, some do have exposure. Sometimes you want to look at hospital-seeking behavior. So you're telling yourself, within the infected, I'll actually have to stratify it further and break my infecteds into two. I want to see the people going to the hospital. I want to see the people not going to the hospital. And sometimes our health systems are not as strong as they ought to be. So there's no access to healthcare for all, even at the hospital level. And so some people do get to the hospital, but they don't get the drug. That is the reality of on the ground. So even within your recovery compartment, you want to check how many people actually recover from getting access to the drug, or rather getting access to the drug, and how many people tend to recover even though they go to the hospital and don't get access to the drug, and how many people recover even without going to the hospital. So you have those who are getting treated, those who are getting treated but not with the actual drug because there's limitation and inadequacy of these drugs, and those who are not getting any treatment. And then you compare the recoveries in terms of the rates, or the proportions, and the deaths, and you then start simulating and you say, what if we advocate for instance, in Kenya here, because health is developed and we have county administrations, some form of governance is devolved. So what if we advocate for the counties to actually invest in health system and purchase this drug and include it in the county integrated development plans? If we have more drugs, does it mean that more people will survive? And then you start assessing the effectiveness of this drug in terms of now the number of deaths in all these three compartments. And then you choose the modeling method. Are you interested in differential or difference? Are you interested in stochastic or deterministic? It depends. Some people say if you have a large enough population, just go for deterministic. If your population is so small, you can go for stochastic. And model quantification, then how do you validate your model? Things like sensitivity analysis come in. And they say statistics and these numbers, they follow logic. If you get a graph that is inverse from what other people have gotten, or it is inverse from what you think is the real case of the disease defining the subject matter, then you should start asking yourself questions. It doesn't mean that you actually developed a robust methodology that actually showed you something that doesn't exist. No. If you actually think that there are more susceptibles around, for instance, case in point, we take a rare disease like maybe sickle cell in a place that is not endemic, and you actually find that there are outbreaks, you should start questioning yourself, because compared to the susceptible, this should almost be like a flattened curve, like a curve at maybe prevalence of 0.4. So understanding the subject matter, the epidemiology, the pathophysiology of the disease is what guides the model development, and not the other way around. Not that if you have the codes in R, they should guide your thinking. No, it's the other way around. So prediction and optimization, and that is the beauty of modeling. You can actually predict future and actually quantify them in terms of resources and tell the government that in the event of an outbreak with this amount of money, I remember in Kenya, they actually predicted El Nino. Then how then do we prepare ourselves for such a case? if they predict drought like it was the case last year, what advised such preparedness? So, and then decision making, that is what we've been talking about. So we have the model parameters, and these are basically the things that then advise or rather hint towards this transitioning from one state variable, one compartment to the next one, so on and so forth. So the first, we've all heard of this from the previous session or before. We have a force of infection. Just think of it as the rate at which susceptible become infected. So if you have a person getting from S to I, it is the force of infection that will get them from S to I. And I'll give us several examples. For instance, if you have COVID, what will make someone get infected by COVID? So this person has to meet with an infected person, this is susceptible. Then what is the probability of them meeting? Or rather, at what contact rate at this, if you're looking at so many people, the infected meeting the susceptible? So at what rate are they meeting? And even when they meet, they don't just get the disease. There's a probability then that when they meet, there's a probability that a disease can be transmitted from the infected to the susceptible. So this is conditional on them meeting. So those are some of the things that we should think of. We should think of is that even upon meeting, that is contact rate, then we multiply by the probability of person getting infected given the contact. So if you're thinking of rabies, let's say for instance rabies, you have a rabid dog has to be rabid. So then what proportions, if you're looking at it deterministic, what proportion of dogs are rabid in the susceptible population of humans? So what is the contact rate between a susceptible human and a rabid dog? So you can just get that averagely on how many bites occur maybe over the total bites or over the total contacts. And then what is the probability that when bitten by a rabid dog, you end up with a rabies infection? So we have all those, and that can actually be gotten from the virulence of this specific virus, rabies virus. What is the virulence in terms of, for each bite, what is the probability that it gets into that? If you're looking at snake bite, what is the probability that a person misses the snake? And what are the proportions of the snakes that are venomous? You have some that are not venomous, others are venomous. And even if they are venomous, what is the probability that when it bites, it actually injects the venom into the system? All these things you get from the ecological studies and previous studies. So the rate of recovery, this parameter depends on the infectious period, as they say. So how long does it take until someone recovers? So if you get a COVID today, it takes you maybe, let's say 2 weeks, for instance. And then the rate of recovery will be 1 over 2 weeks. Something very important is that when you're modeling, all your units have to be standard. If you're modeling in days, all your parameters have to be defined in days or % days. Even if you're looking at the hazard, they have to be in days. So if then you're given a recovery in years, you have to convert them to days. So rate of infectivity for diseases with exposure now, how long does it take an exposed person for them to seroconvert and become infectious? And then the inverse of that will be the rate of infectivity. Loss of immunity, and that is what now defines a person getting from R to S or I back to S. So reciprocal of the time period one remains immune before, susceptible after recovery. So if you're infected with, let's say, malaria, and then you're taking the drugs, you're done with the drugs, you're recovered. But let's say maybe the drug components, rather compounds, if you look at the pharmacodynamics of the drug, maybe it is said that they remain in the system for a certain period of time. And during that certain period of time, you cannot get infected because they're still in the system. If that plays a role in immunity, then how long does it take before the immunity wears off? The birth and the death rates, so it is said, but mostly when you're modeling, we have endemic and epidemic diseases. So when you're modeling endemic diseases are diseases that are known to be there. Let's think of malaria in our case, East Africa. They are known to be there. Let's think of diseases that take a long time, like maybe TB, tuberculosis, that take a long time, chronic diseases and endemic diseases. If you're modeling these diseases, it is important to include demographic factors like births and deaths in this compartment. Because someone who has TB and they die of an accident, road accident, did they die of TB? Yet they are in the infected compartment. No, this is not disease-induced deaths. These are natural deaths, other deaths from causes other than TB. So then you have to factor them in all these compartments. So let's say then we dive into the practical. But before the practical, we'll just touch on like 4 slides on the reproductive number, which is an important component in quantifying whether there will be an outbreak or not. So we say that this is one of the most important aspects of epidemic modeling. And it actually estimates the threshold condition for persistence of an infectious disease in the population. So what is a reproductive number in a disease setting? If you have the disease, how many people do you infect if you're infectious? And how many people do I infect? If I infect 2, you infect 3, another person maybe infects 4, another one 5, on average maybe infected 4. So number of secondary infections from a primary infection, on average, if the average number is 4, then that is the basic reproductive number. Just think of it that way. And what does that tell us? If on average, an infected person can infect more than 1, then there's a possibility of an outbreak. If on average, an infected person infects less than 1, then the disease will definitely die off in the population, or maybe remain endemic at some level. And so is the case if a person just infects 1. So that is what defines an outbreak. You want to see, does the infected on average infect more than 1 person? And if it's an epidemic, and like we have diseases that are seasonal, diseases like maybe influenza, we see most of it during the cold season. And if the disease is SIR and confers long life immunity, the more the infected, the more the infected, the more the infectious, and the more the people will be infected. So you have your R not greater than 1 until at some point where the susceptible are now getting lower or rather less compared to the infected. And then you have your graph now starting to flatten and then going downwards because there are no more people to infect. People are recovering and they're having long life immunity. And it varies from disease to disease. So the disease may also become endemic, leading to attainment of an endemic level. We have actually formulas that have been actually proposed for measuring endemicity of these diseases. Case in point, we look at SIR epidemic and we look at SIR endemic model. And then we want to see where did this formula come from. These are not formula in both these scenarios where the disease is endemic or epidemic clear from the population. So we have the susceptible who are getting infected and going to the I compartment. That rate are divided by N, and these are frequently dependent disease because we are dividing by the total population. And then the I then can recover rate, I hope, gamma. So then we let the number of susceptible be the susceptible at time t, IT be the infected at time t, and RT will be the recovered at time t. Now think of it this way. Assume that we don't have deaths at this point. So in this population, you can either be susceptible, infected, or have recovered from the disease. In this whole population, definitely you just fall in either of the 3 compartments. Therefore, here we say that the total population N is a summation of those who are susceptible at that specific MP, plus the infected at that MP, plus the recovered at time T. that makes up the total population. But then how do we assess whether we are going to have an outbreak or not? And you're seeing that these are the differential equations from that specific. We are saying that this person who moves from S to I, so this is a force of infection of the S. And this S person susceptible has to interact with the I for them to become infected. And that is why we have beta SI. So when a susceptible meets an infected, at a force of infection beta, they become infected. Because it's a frequency dependent, we divide by N. And it's a minus because it gets people from S. And remember, this is an S compartment. We are trying to see how it changes over time. So they move, this is the number of people who will move. And these people who are moving, where are they headed to? They're headed to I. And that is why when this chunk here comes to the I, it is now a positive number because they are now off from this compartment to the I compartment. But hey, we are also losing people in the I into the R. So people are recovering at rate gamma. And who is this person? Who are these people who are recovering? The infected. And that is why we are actually multiplying the gamma recovery rate of the infected. You can't recover when you've already recovered. And that is why Sylvia actually said that one of the best hacks she has, or rather she's learned, is that you multiply the parameter with the preceding compartment. That is why in density dependent here, you'll only see B, is it BI, because of BS, I've forgotten. And then these people who have recovered are leaving this I compartment and going where? Going to the R recovery compartment, or recovered compartment. And that gives us the set of grouping equations for the SIR epidemic. So you want to see then what defines an outbreak. And we've said that this person who is infected, for an outbreak to be there, they have to infect, or a disease to be there, they have to infect greater than 0, say 1 person or 2. So we want to take this formula here that defines the infected and use it to calculate the, sorry, I'll just get this out of here, and use it to calculate the basic reproductive number. And just step by step, you're saying that from this calculation, you're saying that the rate of change in the infected has to be greater than 0 for there to be an outbreak or there to be a disease. So if you look at the infected today and tomorrow, it has to be the change between today and tomorrow. You can't get less than 0. The disease will die off. If you get greater than 0, then it means that the disease will still be there. But what is it that we've used to refer to change in I over time? We've used this specific notation. So the right-hand side is equal to the left-hand side. So you're saying that the change in S, so you're saying, sorry, the beta SI over N has to be greater than 0. It has to be greater than 0. And here we are saying that, so it is minus, sorry, it is minus the recovery. So I think this is slightly ahead. So if you think of it, I'll just type here. If you think of it this way, this particular portion is greater than 0, right? That means that this is also greater than 0, but we're using the right-hand side. So if we take this particular part to the other side, it will be plus gamma I. So we'll have beta over NSI being greater than gamma I because we've actually crossed it to the other side. And that is what we have here. This is that. So if we bring this specific part here we'll have, because it's positive, it will come to minus gamma I greater than 0. So then we find likely terms and cancel them out. Here we have I, and this other side we have I. We'll cancel them out. And so we are saying that beta S over N is greater than, that's the parameter, gamma. And we are saying that in the beginning, or rather the beginning of the disease, we assume that, like in COVID, only 1 person was introduced into Uganda with COVID, and that's how people started getting infected. Maybe they came from a place that had a COVID outbreak. So in the beginning, the number of susceptible, in the beginning, is close to the number of n. It's so big that it's comparable to n. Because if you take maybe the population of Kenya, it's 52 million, and you just bring one person, 2 million minus 1 is close to 52 million, which is n. So then we can always compare the beginning s to n. And when you compare s to n at the beginning, then we can have this s being substituted by n, and then we cancel out the n. So that is what we are saying here. In the beginning, this s is close to n. And then we can just cancel out the n's, and we have beta. And so if we have beta greater than alpha, now this part we bring it. So the greater than gamma, and then we divide both sides by gamma. Here we'll get gamma is equal to 1, and here we get beta over gamma. And that is the basic reproductive number formula. You want to get the rate of transmission from S to I, how frequently people are getting infected, divided by how frequently people are getting recovered. If, for instance, 2 people get infected between today and tomorrow, and one person just recovers, it's 2 over 1. So that is actually how the formula was. And it makes sense. How frequently people are getting infected divided by how frequently people are getting recovered from the disease. What if then we have endemic model? You say that in an endemic model, it is there. Endemic disease, sorry, it is there in the population. And people can die of other causes other than disease-induced deaths or other cause of death. So we want to factor in the death in the susceptible. We want to factor in the deaths, background deaths in the infected, and we want to factor in the background deaths in the recovery. And we want to factor in the births. And here we are assuming that the birth rate is equal to the death rate in the cycle population. And so people are coming in at that rate of births in the natural population, and they're dying natural causes of death in the susceptible at rate mu. So how does our formula change then? That in that case, in the previous case, we only had this one. But here, we are also bringing in people because of births. And we are losing them because of natural deaths in the susceptible population. So that is the only change, is that we are factoring in the demographic processes. And therefore, these people who are infected are the ones who will go to the I compartment. But remember, this I, they also recover at that rate, but they can also die based on natural death or other causes of death, which are not disease-induced. And we have the recovery who move from I at that rate of I minus their deaths, natural deaths. Then how do we calculate? Just the same thing. We now move with this one here, the specific formula that denotes DIDT. Change in T is what defines, change in I, sorry, is what defines whether there'll be an outbreak or not. And that is why that is the specific formula of interest when calculating the R0. And if DIDT is greater than 0, there'll be a disease. And we are seeing that the DIDT is those who are infected, minus those who recover, minus those who die of other causes. And here we can see some like terms here. So we have the I's. We just want to factor out the I in this specific component. And if we have I outside, because negative times, so here if we bring it out, it will be a negative. Negative times a positive is a negative. So we'll have these parameters added and multiplied by I, which is factored out for ease of manipulation. So we just want to bring this other part the other side, and because it goes as a negative and crosses the bridge to the other side, it gets to there as a positive. And so what are the like terms? We want to cancel out the i's, and we have beta over ns, or rather beta s over n, being greater now than the rate parameters. Now we are also considering the natural deaths in that population. And so what's next from that? We say that at the beginning of the disease, the number of susceptible are comparable to N. So then we can just assume it when the disease starts, the S was close to N, in fact, and cancel them out so that we have the transmission rate from the susceptible to the infected being compared to these parameters. And if we divide both sides by this will cancel, we'll get 1, and this will be beta over, that is gamma, the rate of recovery still, plus now the natural death, which reduces the number of infected as well. And that is the R0, and that is how the R0 differs from an endemic disease to an epidemic disease. It's just that in the denominator, we add the rate mu, which stands for the natural deaths. I think that's it. Until there, I'll get some questions before we head to the practicals. Thank you. I think we do how many? We do, if there are questions. Yeah.
Thank you so much, Mr. Ofete. You can go back to the last slide. It's just something I need to get clarity on. Last slide, I think, after this one, the slide after this one, as you're calculating R0. I beg your pardon on how this susceptible changes to an N. You said something, you made an assumption that happens at the beginning of the disease. It's what I did get.
Yeah, thank you so much for that question. At the beginning of the disease, I just gave an example of how COVID started in Uganda. So how COVID started in Kenya is that this morning we wake up and then we hear that some lady has tested positive and she was coming from somewhere. And there was no COVID in Kenya at that particular moment. So how many cases of infected do we have? Only 1. The remaining population, say 52 million, was susceptible now, and they're not infected. So, but the total population of Kenya at this particular moment is 52 million plus this 1 person. So what the formula assumes that at the beginning of the disease, when we have this 1 person being introduced into the disease, or this 1 case, the number of susceptible comparable to the total population, it's so huge that it's comparable. It's like 99.9999%. So then you just assume, clear. Yeah, and you cancel them out.
Thank you. That's clear.
Thanks. Anyone else? Question, clarification, as I said, is a discussion. Okay, if there's no question, then we head to our practical for today. For today, we want to see then how to describe our model. They say that the description of your model should be clear enough to make someone else reproduce that model in terms of the compartmental flow diagram. So think of it, you're applying for this grant and you're proposing to use a compartmental model diagram. And they want a 1-pager, maybe diagrams are not allowed, but you just want to describe whatever you're going to model in terms of the flow of the disease through the compartments. So they say that how you describe, it should be clear enough to make someone draw a compartmental diagram of what you had envisioned. And if I give you a compartmental diagram like this one, like this one, let's say this one, you should be able to describe it in a way such that when you give me the description or give a third party the description, they can be able to draw the same thing as is what you'd envisioned or rather described. So that is the practical for today. We're just going to improve our skills on describing this flow diagram through the compartments. And for today, we have a case on malaria model description. And this particular example says that susceptible humans become exposed to malaria when bitten by infected mosquitoes. And this transition is determined by the transmission rate parameter, which is also known as effective human mosquito contact rate. Effective because it ends up for infection. from mosquito to humans, and it was denoted as the beta of humans. That means that it's the beta, the humans who are getting infected here. Individuals in the exposed compartment progressed to being infected humans due to the incubation period at race alpha. So that's how they move from the infected to from the exposed to the infected. And when they're infected, they eventually recover from malaria due to treatment or their immune system's response. The transition is represented by recovery rate parameter for humans, which is gamma. So they've now recovered. In this example, recovered individuals become reinfected as soon after waning off of their immunity. Sorry for that. And the duration that it takes for the immunity to wane off is actually D days. So we are considering them all these parameters in units of days. So we also have something on mosquito. We are saying that susceptible mosquitoes become infected when they feed on infected humans. This transition is determined by transmission rate parameter from humans to mosquito, now denoted by the beta, which is force of infection for mosquitoes. Mosquito in the infected mosquito compartment do not transition or rather transit further in this basic model, as they can transmit the disease to susceptible humans when they bite. So we have mosquito from S, or rather susceptible to the infected, and they can only transmit to the humans. And we have humans who are getting bitten by mosquito, which are infected, and then they go transit to the infected, and then to the recovered, and back to the susceptible after D days. So we want to think of it this way, and we want to draw a compartmental model diagram for this description. And then after that, we'll get someone else to describe the diagram that has been drawn. And if we have time, then someone will just give a basic model diagram, and we will let someone describe it from us other than mosquito. So any volunteer? I was thinking of maybe how many are we? We are 12. I was thinking of pairing us up. We can do threes. So maybe we do any suggestion first on how to go about this?
I think it can be individual because literally everyone is in a different location. So even if you pair us up, we can't work together.
Okay. I was banking on breakout rooms, but if that's the case, it's okay. Then I think we do 10 minutes and meet at 3 or 5, sorry. 3 or 5 with the diagram, just the diagram. Yeah, so we are back. I don't know if just choose on someone randomly. Are you in a position to speak? You? Hello? Gabriel? Are you done, Gabriel? Jessica? Jessica, are you in a position to share what you've done?
Requesting for some more 5 minutes.
5 more minutes. So I didn't get that clearly, Ross. Okay, it seems like she said 5 more minutes. So we have until
Saying something.
I seem not to get Proskovia clearly. But let's do until 12 past 3 then. So let's have someone share with us what they've drawn. Anyone who's willing, I'll stop sharing my screen. I'll go with Ibrahim. Ibrahim, you're the name that I've just seen on my screen. Are you in a position to share your model diagram, Ibrahim?
Dr. Robert, I don't hear you. I don't know if it's my problem. There's someone here, Dr. Robert.
Can anyone hear
Can
me?
you hear what Dr. Robert is saying?
Robert, you're very clear.
Oh, thank you. So I'm looking for any volunteer. Anyone? John? You're
Okay,
my
Robert.
countryman. Maybe you save me.
Because of time, I can share my screen.
Please do, Brian.
Though I had not yet finished putting the label parameters, but I'll try to explain something.
Sure. So just
Okay.
just put it and tell us what you wanted to do, and then we'll have a very different person trying to describe whatever you've drawn, okay?
Okay, this is it.
Okay.
I hope you can see it.
Yeah, I can see it, but I think the upper part is
No, there is nothing actually in the upper part. Start from there now.
okay, yeah.
Like you said, there is malaria that is affecting people. Then there are mosquitoes, the vector, that are susceptible to getting malaria also. So I drew two models in one for the vectors. SV means vector. Then this part here, SV and IV means the one for the what? For the vectors. Then SH and IH mean the one for the individuals. So maybe I didn't put the parameters, but what I can say, starting from up here is the birth rate. Those who enter the model to get susceptible. Assuming maybe they entered the parameter beta into the susceptible. Then of course there are those who will die, natural death on this one, assuming it is mu. Then those who move from susceptible to get infected can also happen at a certain rate of maybe theta. Then there are those who will die, natural death here. Then of course with malaria, there are those who will recover. Are we together? So
Yeah.
now when it comes to the vector, the malaria vector here, there are those, of course the vector also has to get born to enter the model. That's why they become susceptible here. This is susceptibility compartment for the vectors. Then they move into the infected if they bite an infected person. Of course, here they will also be exiting because of natural death. Even here, there will be an exit because of natural death, but there's no recovery for the vector.
No recovery for the vector.
Yeah, so this cross and this one shows mosquitoes may be biting the human beings. That's transmission that happens between the vectors and the vectors. So that was my reasoning about the model. You can advise. Thank you.
Thank you so much, Brian. I'll request you to keep sharing your screen and nominate one person. We need one person to try and describe whatever they can get out of this, get a description out of this.
Maybe, Robert, before the description, could we have more input on the model diagram, on the model flow?
Yeah, sure. In terms of parameters, transition parameters.
Yeah.
Okay, then Brian, maybe you can just add the transition parameters. I think that's the only thing that's pending from your model.
Yeah, okay, then I'll have to take some time to add the parameters because I didn't put them because of time.
Okay. No
stop
worries. We
sharing.
can give you until 3:20 if that's okay with you. And then we just proceed with your model.
Oh, then maybe someone in the meantime can be sharing their work. Let me stop sharing.
Yeah. Okay. Anyone else who feels free? As I say, this is a discussion platform. We are here to improve our skills and knowledge with regards to dynamic modeling. So it's a discussion. Anyone who wants to share their work, you can go ahead, as Brian is including parameters to his model.
My model looks a bit different from Brian's, but I have not yet done the labeling.
Thank you, Jessica. Just share. We want to see the difference. That is actually a point of learning.
Yeah, that is what I'd come up with.
Okay, just maximize your screen a little bit.
Just a minute. Is it maximized now?
You can just zoom in if you're in a position to, but that's okay if you're not in a position to. Yeah, there. Okay.
Yeah. Now this compartment is for the susceptible humans. This for the exposed humans, infected humans, and then the recovered humans. So susceptible mosquitoes and then the infected mosquito. Yeah. Then I include the parameters.
Yes, so I can see there's something coming from infected mosquito towards the recovered.
Oh, no, this is coming from the susceptible mosquitoes to sorry, it is supposed to come here to the infected compartment.
The infected, okay. So from susceptible to the infected compartment. Okay. Yes. Yeah, and then we have infected mosquito to the susceptible.
Yes.
So, and which arrow is the susceptible to infected mosquito to infected humans pointing?
This is pointing from the infected mosquitoes to the susceptible mosquitoes.
Infected?
Infected mosquitoes to the susceptible humans, sorry.
And then from infected humans, from susceptible mosquito to infected humans?
Yes.
Okay. Thank you so much. So the difference you're seeing here is that she's actually included the exposed compartment. And something else is that we have actually the same arrows that we had in terms of the transitions from the mosquito to the human. And we don't have the backgrounds, demographic factors in terms of death and birth. Thank you so much, Jessica. Thank you so much, Jessica. Maybe you can just wind up on your model, finish up on your model. As you see, Brian, are we done?
I'm about to get done.
Okay. Just feel free to share your screen as soon as you're done.
Okay, let me.
Thanks, Brian. Maybe you can nominate one person to help you describe the model. you need an independent person who is not you. So maybe
Okay,
other than
maybe.
Jessica.
Proceed, if Proceed is there.
Yeah, Proscovia, maybe you can help us describe this model.
Hello. So according to this model, we are looking at SH, which is the susceptible population among the humans, and mu looks like the birth rate of the people entering the humans, and then theta is the death rate, then the death rate due to other reasons. And this moves, I think we are missing the exposed compartment here. So this moves to the exposed compartment according to the statement that they gave us using beta, the rate of using beta. And then from the exposed, we move to the infected compartment of humans, which continues to the recovered compartment of humans using, what do they call this thing? It looks like an E. Yeah, and then beta looks like the death rate due to other reasons. Yeah, and then we have gamma, which looks like the death rate due to other reasons too. And then we continue. We continue up and look at the susceptible population of the vectors or the mosquitoes. And then we look at theta V being the birth rate of the vectors. And then we look at alpha V being the death rate due to other reasons. And then we look at WV, which looks like the rate of infection from the susceptible compartment to the infected compartment. And then we look at gamma V, which looks like the death rate due to other reasons. And then there is this line that moves from the infected vectors to the susceptible humans, which means that these infected mosquitoes will bite the susceptible humans to move to so that the humans can move to the infected compartment. And then we have this line that runs from IH to SB, which means that mosquitoes that do not have malaria bite infected humans and then get malaria, hence moving to the infected vectors compartment. Yeah, that's my explanation of this model.
Thank you so much.
Thank you so much, Professor.
Yeah, I'll request you, Pros, to leave your mic open for a while. Just a few follow-up questions for yourself. Now, okay. How did you tell that it is the infected mosquito that is biting the susceptible human? Imagining that you didn't know this is a mosquito. Yeah.
I've not got the question well.
So you say the IV to the SH line, it is the infected mosquito, yes, biting the susceptible human. So is it your background knowledge that informed you of that, or is it the model that informed you of that?
Actually, it's my background knowledge because I'm not seeing an arrow that runs from either of the two. Yes, I used my background understanding.
Thank you, Prof. That's one mistake we've noted, an arrow. What other mistakes have you noted from this model as you're explaining? What
I think we missed the exposure.
Yeah.
We missed the exposure compartment. And then another thing is these death rates due to other reasons should be the same. They should have the same symbol throughout so that we can have a particular death rate due to malaria on the compartments of infected. For example, IH should have a particular, for example, mu-M specifically for malaria, and then for all the compartments, we should have mu-D for all the other compartments to show death due to other reasons. And then for IV, we need to have a death of mosquitoes due to malaria. So maybe it could be mu-V and then a normal mu for SV and IV to show the death of mosquitoes due to other reasons.
Thank you so much. Yeah, thank you so much, Proscovia and Brian for this. Brian, I'll still request you to share your screen for additional. Yeah, he did a marvelous work, but there's some things that are slightly amiss that we have to learn from this, is that the arrow should indicate where we are headed to and how these compartments are relating. Remember, it's called transitioning. So we don't know from where to where are we headed to. So remember, when you are sending this, you're sending this to a layman who has to understand as much as possible what you're trying to insinuate. And we don't have an exposed compartment, which should actually be there. Something else is that we wanted a model out of our description. And that's clearly missing, because remember the second part of this task was for someone to write this description, and then we compare the description with what I had shared. And the similarity between the second person's description from your model and the description that is shared should actually tell us the amount of work you put in terms of accuracy. So they should be similar. So there's a miss on the parameters that you've used, which doesn't really, there's no specific parameter you should use, but for this case, they are not the parameters specified in the practicals. And then we didn't have the backgrounds, but thanks for including the backgrounds. I just had one question before we go back to the actual diagram on how it should look like. What would make you include the alpha V? Oh, and thank you, pros, for that. If you are referring to something common, say, so you have to reduce the number of parameters as much as possible. If it's mu for the background, that has to be mu. If you have, if you are using proportions rather than, if you're using proportions and you have two complementary compartments, where one is death, the other is survival. If you're using theta for deaths, you'd rather use 1 minus theta for the survival rate. So those are the basics. So Brian, what
you mean from the SH, if I use mu here, I should use 1 minus mu here?
No. Sorry for that. All these are bats, and the bat of mosquitoes totally different from birth rate of humans.
Yeah, that's what I'm trying to do.
So I'm saying, okay, if you're having, if you're simulating the effectiveness of an intervention, and you have one compartment with the intervention, the other compartment without the intervention, where maybe, let's say you have sick individuals, people being transported by accidents, people being transported by ambulance, and those not being transported by ambulance. You're assessing the impact of ambulance, right, in averting deaths. So if theta is the rate of those who are being transported by ambulance, definitely all the other accidents from I are those who are being transported, right? So in that case, you'd rather just use 1 minus theta, and that person will know that definitely this plus this is equals to 1. Or if you're using different, you add them as model constraints. You're saying if the other one was gamma, theta plus gamma is equals to 1. But I wish I had that example. So Brian, I wanted you to tell us why, or rather what interventions would bring the alpha V.
Sorry, I had lost my network.
Sorry for that. Deaths in the mosquito compartment, right?
Okay.
There's deaths in the mosquito compartment.
Yes.
So other than background deaths, what other interventions could come in there?
I think I missed your question completely, Doctor.
So we have deaths in the mosquito compartment. We are losing mosquitoes that are dying.
Yeah, at this rate.
Yeah.
That's
So other than background deaths, what interventions do we have in place that can cause mosquito to die?
we can be doing the indoor residue spraying.
Yeah.
Yeah,
exactly. We can do sprays, we can do treated mosquito nets, right?
But those ones will not cause them to die. If the mosquito nets are treated, yes.
Treated, yeah. So if we do treated mosquito nets or just mosquito nets, and we do indoor spraying, how will that affect the number of infected humans?
The number of affected humans will reduce.
Exactly. So those interventions will affect parameter transitioning from SV to
SH.
So it will actually be from IV to SH, right?
Yeah.
So one way of testing an intervention is you want to test, and we are missing actually a parameter there. We want to test how much it reduces a force of infection. So if you say, if maybe studies have shown that if you sleep under mosquito nets and you do indoor spraying, let's say first, if you sleep under a mosquito net, your chances of being bitten by a mosquito reduce by maybe 30%, because maybe you spend 70% inside the mosquito net. And if you do indoor spraying, it reduces further by 90%. So that percentage that it reduces by is what then you apply to your transition parameter. So that's one way of assessing for intervention. I'm not sure if that's clear.
That's clear, Doctor.
Thank you. Now let me share. Thank you so much thank you so much for that.
Hello. I had a question.
Please. Yes,
so
please.
Where would larviciding, under which compartment would larviciding affect?
Larvicidal agents, when you're killing mosquitoes.
Yes, because you're killing the larvae.
Okay. Let me see your diagram again, Brian. So if we had introduction into the mosquito, so what is theta V, Brian? What is theta into the susceptible vectors, susceptible mosquito?
Here.
Yeah.
This theta V. This is the rate at which mosquitoes enter into the susceptible compartment. Either through natural birth.
Yeah. So if we have larvicidal agents, they are affecting mosquitoes that are being included into the population. So if then you assume, yeah, exactly.
So you're affecting this theta or pi?
Theta V. Yeah. So, yeah.
All right. Thank you.
Okay, now I'll share my screen. Thank you so
Actually,
much.
Robert, before you share,
yeah,
in your description, there's where you had noted that those who recovered, the recovered individuals, no, the infected human is progressed to recovered, but then there is where you noted that the recovered individuals, they get to be infected. Again, I'm trying to remember the story very well.
Yeah, they go back to susceptible after D duration D.
Yes, okay. I had reflected that arrow.
Yeah. Thank you for that, Abel. I'd missed on that. And actually the point here was, other than actually showing the arrow coming back from, maybe you can just share your diagram again. Let me just share this diagram. So I got this description from I tried to describe this. This is what I tried to describe. I'm not sure if you can see my screen.
Yeah, we can see it.
Yeah, but the parameters I changed. I didn't want it to look complex, so I didn't include the background. So these people are going back. These people are going back to the susceptible, from the recovered to the susceptible compartment at duration B. And remember, we said that the rate of waning off of immunity, the rate at which a recovered person goes back to the susceptible, is an inverse of the duration. So I expected to see 1/D instead of D. That was the catch, just to tell us that it's an inverse of the duration of time. Is that clear?
Yeah, for me, it is very clear. Thank you so much.
Thank you. And something else is that we have the S going to the E. I think we mentioned beta. And then we have the E going back to, we're going to the I at, I think, rate alpha. And then we had, I'm talking of our rates, not these ones here. And then we had this at the same rate gamma. And then we had these people going back there at duration B. So this should be rate 1/D. So something to note is that these compartments are similar in terms of the notations, but then we have subscripts that actually specify whether it's a human or a mosquito compartment. So that was important. And we have the arrows indicating the direction.
Yeah, something, Robert, there. I think in my diagram, I had missed the exposed compartment at vector, no, and the lower one. Did you include that because of the background knowledge, for example, that I know this can be a susceptible mosquito which has bitten the infected human being? It can be exposed but not infected. Did you use the background knowledge?
Now, this is not my diagram, this is a publication. I actually didn't include it in my description. I just left it out.
Okay.
Yeah, to make it simple.
Okay.
Yeah, and thank you for noting that. And then we have the same force of infection using beta, but now we are reducing the number of parameters. So, and this is one of the things that we mentioned. So we are using beta for the same force of infection, but denoting with a subscript that actually tells us whether this is a force of infection for the vector compartment or for the human compartment. Something else is and there's been a battle on lines crossing. There's been a battle on lines crossing, but here you can't do away with it. And you can see the lines are dotted. So I'll just say one thing about the dotted. But first, here, the direction actually tells you it is the infected humans who are actually affecting or rather impacting on the susceptible mosquito. Will then go there, and then after being infected, they go and bite the susceptible humans. So that is very important. And you'll see in some publications, I'm not sure if I can draw here. Yeah, I think I can draw. You'll see in some publication, this is an S, this is an I, this is an R, but there's a dotted line that comes like this. It doesn't have to be, there's a dotted line that comes like this. I'm not sure if you've seen that. So that basically means that the transition from S to I, or rather from S to E if it's SER, or S to I if it's SIR, is actually affected, or rather determined by the number of I's. So like a case in point COVID, some publication did this. So that's just tell us that the more the I, the more the higher the frequency of transmission, or the rate of transmission outside S. Any question? Any question? If no question, I just want to thank you for your time and to thank Abel for the opportunity to share and discuss with the team about dynamic modeling. And I hope to learn more throughout the week. Back to you, Abel.
Thank you so much. I was curious that maybe the next slide is going to have equations, because of course in the description we have captured some of the equations, but I was curious to see if we have some bit of equations as well. We have more 19, no, we have extended by 11 minutes. But do you think we can tackle that, say, in our practicals tomorrow? Do you have that in mind? Robert, I'm not sure whether we have you tomorrow or Wednesday. Let me just double check. Because this has been very colorful.
Yeah, we can have questions from the same.
Robert, are you saying something?
No. Sorry, I actually had a problem with my internet.
Okay, yeah, I think we have you again. We have you again tomorrow. We have another discussion with you. This has been very colorful. I want to request that tomorrow we advance to equations before we go to the validation of our model. Is that okay? Is that okay, Robert?
Sorry, Abel, so sorry. I had a problem with my internet. Do you mind repeating what you just said?
No, yeah, I was saying this has been a very good and a very interactive session. Is it okay tomorrow you have something on, we proceed with the same, this has been a very interactive, maybe you can get another one, but this is very good. But next time we advance to having the equation is developed as well.
Okay, we'll just develop equations for the same model tomorrow then. Tomorrow at what time, or Wednesday?
No, it is tomorrow. We have you tomorrow at 1:30 to 3 p.m.
Sure. Then tomorrow we develop the equations and see how they look like.
Yeah, this is very good. Yeah, and thank you so much. I want to request my colleague Winnie to give a vote of thanks to you. Winnie, you're welcome.
Thank you so much, Abel, for giving me this opportunity. I'd like to thank you, Robert and Sylvia, and our moderators, Proscovia, for today's session. Really wonderful and insightful and educative, and we look forward to having more classes with you and implementing or integrating this modeling aspect into our different work which we do, the PhD student, master students, and in our projects. Thank you so much for your time, Robert. Thank you, Sylvia, for your time. Really appreciate it. Thank you. And thank you, members, also for giving us time, for being present up to this time.
Thank you, Winnie. My pleasure.
Yeah, so thank you so much, colleagues, and we will stop it here. We'll meet tomorrow at 9 a.m.